So hello everyone, it's the lab number 2. So today we're going to study integrators. Integrators are special type of op-amps. For the feedback loop we use a capacitor. So remember, for inverting type of op-amps, operation amplifier, we connect the positive input to the ground and connect the input signal from the signal generator to the resistor of 1K. But feedback loop is not connected to the resistor, but it's actually connected to the capacitor. So you see from the out it goes back to the capacitor and then it comes back again to the negative input. So choose the smallest capacitor here. We can have, so it's 0.01 microfarad. So this is a topology of the integrator. So integrator is basically the type of op-amp that integrates the input signal. So let's see, if we have like the yellow and blue line are the same, so both of them are sinusoidal cosine waveforms. So set them in your signal generator 1 kHz frequency and 1 volts peak to peak waveform. So here in output we can see that actually the input and output signals are actually different. So here the blue line is 1 volts peak to peak cosine, but in output we're having actually amplified sinusoidal signal, as you can see. So the integral of the cosine actually is this sine, and the integration of sine wave is a cosine wave. So as you can see, the integrator is working here, and how it should supposed to work. And so basically why it works like this, as we know, integration is area of the under the line or any function. So basically, as we can see, for the input signal, since it's inverting type, so it's gonna do opposite output. So we can see the area above the blue line of input signal is actually decreasing with the time, and up to 0 we can see the area of output actually increasing. So since it's inverting type, so the area in output is going to increase up while the input signal is decreasing to 0. But once it's crossed the 0 and goes to positive, the area of the output signal actually is gonna decreasing, as you can see in the 0 line, in 0 point. Area of the blue line is actually increasing, but area of the yellow line is decreasing. So basically it's integration. So we can have integrated function here, and this is how the integrators work. So your goal is to repeat the same topology. So you should make the integrator here. Basically it's the same topology that we did before in the first swap, but you just replace the feedback resistor with the feedback capacitor. Set your frequency 1 kHz, 1 volt peak to peak. Observe the output signal and set your DC biasing to 20 volt. So let's see what happens if we decrease this biasing from 20 to 10, like say with a step of 1 volt. So you can see the output signal actually is clipping. Once reached to 10, it start to creep. So as you can see, for this configuration we should have actually even much bigger the biasing. So we'll keep it back to the 20 to see the same full sinusoidal waveform. Also try to see what happens if we gonna change the frequency. Let's say from 1 kHz to 10 kHz. We're gonna increase. Change. So as you can see, so I just switched over the signal. Yes, as we can see, with increasing frequency, actually the amplitude of signal is decreasing and almost getting flat, and actually it goes up. This is due to the bandwidth of the amplifier. But if we're going back to 1, come back to the sinusoidal signal. Now let's see what's gonna happen if we're gonna change input signal to different waveforms. So let's say what will gonna happen if we integrate the square. So as we can see, input was square, but output is actually the ramp. And so integration, if we integrate the function, the square function, we're gonna have in output actually this ramp signal. Ramp signal is goes like triangle signal, up and down, up and down. And actually this makes sense because as we can see here, so as we can see here, in the input signal, we can see the area is continuously increasing. In the same time, output shows that area is continuously decreasing. But once the area drops to negative, so it's a slight, it's drastically changes to the negative. The area reaches to the maximum. But then area starts increasing. The area of the output is starting decreasing. So it's opposite integration since it's inverting upon configuration. So we have the integration as it is. So the integration of the square signal function is giving us the triangle function. Same things is happening if we change input as now input is a triangle, but now what the integration of the triangle function gives action for us is gives actually sinusoidal signal, as we can see. So in the negative part the area is decreasing, but output shows that it's increasing. Then once it's crossed the zero, it shows that it's increasing. The area of output is decreasing. So this is also the same way how the integration of the function is happening. So this is what integrator is doing. So try to repeat same procedure. Try to make the topology of the integrator. Choose for input signal, sinusoidal, square signal, and triangle signal, and record and make the pictures and photo of the waveform what you get, and make the report and record all your data that you recorded during this session of integrator OpAmp.